Then we'll move on to chapter 9, at least the initial part of that, radiation. Because we get behind the schedule. Now we talk about wave. Obviously, we want to know how you can excite wave. So that is all related to the radiation problem. And obviously, you need charge density or current density to excite wave, or charge to excite wave. So movement of the charge will show that the movement charge is responsible for radiation. But we'll use the formula that we did in chapter 6 as the beginning. So next we start with equation 9.2, which is what we did in chapter 6. Remember that we divide this formula as we'll consider the vector potential, not the scalar potential. There's a reason for that. It will be a homework problem to talk about mu zero, and then integrate the current density to pi, d pi, and then evaluate the retarded time divided by R. And R is defined as epsilon x minus. Right. And the retarded, where retarded bracket means retarded bracket actually means t pi change to t minus R. Evaluate that. So you can, in some sense, you can change it to, instead of using a retarded bracket, you can use the, I think I have to do another integration, t pi. This is j x pi t pi, and then put this as delta function t pi minus t plus r, which is x minus x pi c, and then divided by r. But this is just the same. I think this is just 9.2 objection. Okay. So this is fine. All right. And now for radiation problem, again, like the wave problem, we usually just consider a single frequency. So everything is proportional e to the minus 1. So we're just using the same omega. Yes, the omega. So especially the J is assuming it's oscillating periodically using a single frequency. If it is not, then you sum over all the different frequencies. So basically a Fourier transform of Fourier series of J in terms of different oscillation frequency. And we consider one at a time, one frequency at a time. Okay, so in that case, you can write J xt as just the spatial part. Okay, to put this into here, but then when you put this into here, just change the x pi, just change the t pi, and you can integrate t pi integration using this delta function, which is the retarded time, and write it out explicitly. But this is dk. Use for 4 pi x pi with j pi. Now this has e to the minus I omega t, because this t pi changed t minus this one. Yeah. This J, this become T minus, so you have T and the minus the other way. Already have a minus sign and plus I omega over C x minus x1, and then divided. This is fine. And then just like what we do in chapter 7, start with chapter 7, define the wave number. Omega over C. Consider just the vacuum first. You haven't considered medium. So you can do radiation. These are considered a vacuum. So just K is omega over C. So you can change that to K. All right. So far so good. And this factor, you can take that out. Take this exponential factor because everything is proportional. That you can say the A xt is also A x multiplied by this factor. So you only need to consider this. A x is different by this one. T I T. Okay, so that's straightforward. And this formula is similar to our magnetostatic consideration when we divide the similar equation for magnetostatic. And in that case, basically, we ignore this exponential factor, basically setting k to 0 or omega to 0. In case the exponential factor is 1, then this formula is exactly what we did for the magnetostatic. Basically, the oscillating current density basically adding this exponential function. Okay, so that is 9.3. And then the other thing, once you have A, you can calculate B, and once you have B, you calculate E using 9.4 and 9.5, which we did before, just like the wave problem. But before we do the full thing, because this is an integral, and this integral usually not easy to evaluate with including this exponential factor, and we would like to simplify it. And the simplification is depends on what how far away you are away from the source, how the length scale depends related to each other. So there we can consider the length scale, how many length scale we have in here. Obviously, you have this J that oscillating within a certain region of space, and assuming it's localized, then you have this the source length, I think it's called D. So basically, this in the integram, this J is confined to a volume with the length scale of D. Obviously, you want to center your integration, the origin as somewhere inside here. So this integration will be 0 if x prime is greater than D, or much greater than D. So that's one length scale. And another length obviously is your observing point. So you observe in some distance x vector, the length of x vector from R, right? Just like the radial coordinate. So that's another length scale. And another one, another length scale is this k. This is a wave number which related to the wave number 2 pi. Right. So you have the wavelength of the wave that you radiate or excite. This lambda, this is a wave. This lambda. Okay. So we have 3-length scaled, and the first comparison will be lambda with respect to d. And if lambda is much greater than d, then it's a long wavelength. And then if lambda is small or even comparable to d, this is a small short wavelength. Right? It's a long wavelength or short wavelength. Usually we consider the case long wavelength case because the short wavelength case, all these integrals complicated. It means that k is large. Right? In the integration that make it difficult. We usually stay with this long wavelength limit, and then even under this long wavelength limit, then there's still a comparison with R. So there are basically the three cases. The one case is so-called far zone. If R is much greater than wavelength and much greater than D, this is what we call is far away. It's called far zone or weight zone or weightation zone. I mean, that's different people call it different names. Right. Right. Yeah, sorry. Much greater. Right. So that's the way to basically. So if you have a lambda is much greater than D anyway, and then that way you consider observing much large as a distance much larger than the wavelength. So beyond that, that's the wavelength or the radiation. Okay, so that's one possibility. Another possibility is so-called near zone, and in the near zone is basically the putting R in between the two. So R is much bigger than D, much smaller than lambda. That's for the near zone. In that case, in this case, because this you're integrating over x prime, so you integrate. So x is R, so basically R is within lambda. So R is outside of this, but this k is 1 over lambda. This difference between the position is roughly, because R is much bigger than D. This is roughly R, but the R is still much smaller than lambda. Or so kr is much smaller than 1. So you can ignore the full exponential function. Exponential function becomes 1. So the formula, this integral is just like the magnetic formula. So that's called a static case. So the near zone or static zone is this limit. So one more is, possibility is D is much smaller than both R and lambda, but R is roughly the same as lambda. That's called the intermediate zone. Okay? And in that case, things are complicated because you cannot ignore that one because R is roughly the same as lambda. So k times this one is not much smaller than 1, so you need to keep the exponential function. That is more difficult, and then you don't have the far zone. So there's other approximation that you cannot use. So the intermediate zone is most complicated. The easiest one turns out to be the far zone, and then you can have a lot of simplification. that is what we'll do for section 2 on time, but this one is starting from section 2. We'll do that. But let me just and then do some this consider some of the intermediate something. But we don't want to do that. Intermediate is too complicated for us. But then there's a final remark. We are using the vector potential rather than scalar potential. We can do the same thing as scalar potential. That's what Jackson did. Using that, and then as it turns out that you get the phi, the scalar potential, and that becomes a charge density instead of current density, right? So you can have a phi potential that proportional to the retarded charge density, total retarded. The lowest mode is the so-called the monopole mode, just the total charge. Instead of the charge density integrate over the whole volume become charge, but you evaluate at the retarded time, which is t whatever t minus let me see, right? However, this doesn't actually have this doesn't give you radiation, and unlike the J. The idea is that if you have a charge density oscillation, but the total charge is still the same, just Q, right? Even if you are evaluate at the retarded time or not retarded time, it's still the same, say the same Q, right? Because it can oscillate, the wave can move, the charge can move around or oscillate, but the total charge doesn't change, right? So and when you're far away from the source, you're still seeing the same charge, and the Gauss law is still valid. The Gauss law is saying that the electric field integrate over the whole volume, or integrate over the surface, is the same as the total charge, but the total charge doesn't change. So that the monopole or the total charge does not give you the radiation. So that's the final remark in this section. So we need to start from at least the dipole term. The monopole term doesn't give you any radiation. Okay, and so that's the end of 9.1.